So welcome to the next topic where we will look at the equilibrium law in a little bit more detail and basically build around that to focus on Le Chatelier's principle and also Gibbs free energy and how you can calculate concentrations using the equilibrium law. So by the end of the unit you should know how Le Chatelier's principle is related to the equilibrium law, how the position of the equilibrium corresponds to a maximum value of entropy or disorder and a minimum value for this Gibbs free energy, and that Gibbs free energy change of a reaction can be both used along with the equilibrium constant using a equation which we're going to be looking over, and the relationship therefore between delta G, the Gibbs free energy or change in Gibbs free energy, and the equilibrium constant. And by the end of the unit, you should also be able to solve homogeneous equilibrium problems using the expression for the equilibrium constant and also calculate using the equation that we're going to investigate. So let's remind ourselves of the equilibrium law. The value of Kc can be expressed for a general equation as such. So as you can see that the concentrations of the product, each to the power of their coefficient, over the concentrations of reactants, also each to the power of their coefficient. So we're going to use this equation to try and solve some concentration questions. Now all concentrations are taken when the system has reached equilibrium, and so given at all concentrations Kc can be calculated. Or if you have Kc, you can work backwards and work out unknown concentrations, which is essentially what we're going to be focusing on today. So first problem up, and for the problems we're only going to focus on homogeneous equilibria, and remembering what homogeneous equilibria are, they are those where the reactants and products are the same phase, so they're all in the gas phase, for example, or all in the aqueous phase. So here we have a reaction, okay, carbon monoxide gas reacting with water vapor to form carbon dioxide and hydrogen. Okay, and the concentrations are given. Remember, of course, that mole equals moles per decimeter cubed. Okay, that's basically what mole, that capital M means, molar. Okay, so given those values, can we actually work out if the Kc for the reaction is 1, what direction will the reaction shift? So pause the video now, let's see if you can work it out for yourself, and then we'll come back and see if you're on the right track. Okay, so the first thing is that we look at the reaction quotient, which we looked at previously in the last topic. And essentially it's going to be plugging in the numbers, substituting the numbers for the concentrations that we've been given. Okay, and therefore getting a equilibrium, getting a reaction quotient of 4. And now we're told that the Kc for the reaction is 1, which obviously is not 4. So because the reaction quotient is greater than the equilibrium constant, the products are in excess and the equilibrium will shift to the left. So you should have immediately realized that we're talking about reaction quotients and from the last topic, and then linked it back to equilibrium constants. So it's kind of going over the material we did in the last topic. Okay, so another homogeneous system you can apply this to is in terms of the dissolving of insoluble salts. Now by definition insoluble salts cannot dissolve, but there is a small amount due to the equilibrium that goes into solution. Okay, because as most of the salt is in the form of MX, so it's basically tends to favor the insoluble salt, the reaction constant, or the equilibrium constant, will not change significantly. It's going to be a very small number. So the more common expression, the solubility product constant that is used is KSP, which is going to be the concentration of M times the concentration of X. Okay, because this guy is going to be a really, really big number in relation to these guys. So similarly, as before, if two ions are given off, then the ion in the equation is squared. So if it was, for example, sodium chloride, then obviously the X part will be squared because you've got now 2Cl minus ions. So the next problem involves the solubility product. What happens if you add 0.5 decimeter cubed of 0.0001 molar solution of sodium hydroxide with 0.5 decimeter cubed of a 0.002 molar concentration of magnesium sulfate? Determine if a precipitate will form. Now the thing you need for that, of course, is the solubility product of magnesium hydroxide, which is 1.8 times 10 to the 11. Okay, and so basically if the answer is less than this, then there should not be a precipitate. And if it is more than this, then it should be a precipitate. So the first thing we have to do is do an equation. So this is the balanced equation. 2 sodium hydroxide plus magnesium sulfate giving sodium sulfate and magnesium hydroxide. And then we have to work out the corresponding concentrations of the hydroxide and magnesium ions, okay, from the values given. Okay, notice here that it is 1 decimeter cubed because we're going to be adding the two volumes together to give an overall volume of, or volume total of 1 decimeter cubed. Okay, so we can tell that the solubility product is going to be 1.8 times 10 to the negative 11. Okay, the constant for the solubility product anyway. If we do the numbers using the equation for the solubility product, you can see that the ionic product itself is going to be less than KSP. Okay, it's going to be 2.5 times 10 to the negative 12. Therefore, there should not be a precipitate of magnesium hydroxide. Right. So that's the case when you have a homogeneous aqueous solution. Okay, but what happens if you want to find an unknown concentration if you're given a Kc value? Well, I'm going to provide a three-step approach, the Rice approach, which we'll go through here, and then we'll do some problems around it to kind of reinforce the learning. The first thing you have to do is write a balanced equation. Fair enough, that's pretty much what you have to do for most things. Okay, and then under the equation, you have to create a table. Okay, so you write in the values of the concentrations of each component using 4 rows: ratio, initial, change, and equilibrium. Okay, so you basically got the rows are going to be going across, which are going to be your ratio, initial, change, and equilibrium, and your columns coming down are going to be your components, your reactants, and your products. Okay, the ratio is the coefficient for the component in the balanced equation. The initial represents the concentration of the reactants at the start. Okay, the initial concentrations. Obviously, the product's concentration is going to be 0 because there has been no reaction yet. The change is going to represent the amount that reacts to reach equilibrium, and a minus sign for reactants represents a decrease in concentration. A plus sign for products represents an increase, and the changes must be multiplied by the ratio of that component. That's why it's important to have the ratio. And finally, the equilibrium values are the concentrations present in the equilibrium mixture. This can be calculated by applying the amount of change to the initial concentration for each component. Okay, so obviously the amount of reactants is going to go down, and the amount of products is going to go from 0 into some other number. It's going to be positive. Okay, and finally, you write the expression for the Kc, or the equilibrium constant, for the balanced equation, and then substitute the equilibrium values into the equation and calculate the equilibrium constant. Okay, so what does this look like in real terms? Well, let's have a practice. Okay, so hydrogen reacts with iodine to form HI. So if 0.1 moles of iodine was reacted in the reaction initially, and only 0.02 detected at equilibrium, what is the equilibrium constant? Okay, so it's all about ratio, initial, change, and equilibrium. The first thing you do is you write down the equation, which I've nicely provided for you, and then you create a table with the Rice. Okay, so for hydrogen, okay, obviously a 1-to-1 molar ratio. You've got iodine and you've got the hydrogen iodide. Okay, so the initial concentration of the hydrogen will be the same as the initial concentration of the iodine, so it's going to be 1 mole. Okay, and 1 mole. Okay, so 1-to-1 ratio. And that's going to make 2 moles of HI. Okay, so it's going to be, from the actual question, 0.1 moles of hydrogen reacting with 0.1 moles of iodine to give nothing at the moment because the reaction hasn't happened. These are the initial concentrations. And then we have the change. Okay, so we're told that the iodine has gone down to 0.02, so we put that in the E column for iodine. Okay, so from those values, you can start plugging in the numbers. Okay, so 0.02 we already know, so that means it's gone from 1 to 0.02. The change has been 0.08 mole. And it's the same, because it's a 1-to-1 ratio, with the hydrogen. So that's going to be the same. And you'll notice that it's going to be plus 0.16 for HI, because you have 2 moles of HI being formed. So 0.08 times 2 is 0.16. So the equilibrium concentration of hydrogen will be the same as the equilibrium concentration of iodine. And of course, HI's gone from 0 to 0.16 plus 0.16. So then we have an equilibrium constant equation. We just plug in the numbers and we get the answer of 64. Okay, that's just an example of how we can find, at least in this case, the equilibrium constant from the question. So you can also find concentrations from the equilibrium constant going backwards. Okay, so concentrations from Kc. Hydrogen reacts with iodine to form HI, just like before. If 0.2 molar of iodine was in the reaction initially and the equilibrium constant was 49.5, what is the concentration of HI at equilibrium? So again, we need an equation, okay? And the little hint I can give you is that you're going to start using algebra. Okay, so the ratios, well, those are the components, the hydrogen, the iodine, and the hydrogen iodide. The ratios we already know from the balanced equation. They're 1, 1, and 2. Okay, the initial is going to be 0.2 and 0.2 for hydrogen and iodine because there's a 1-to-1 molar ratio, and the concentration of HI is going to be 0 because it hasn't reacted yet. So the change is getting a little bit more funky. Okay, so when writing X, use whole number ratio. So rather than saying, well, what's the change going to be, we're saying the change is going to be X. Okay, so we just plug in those values again. Okay, so change is going to be minus X. Okay, the change in concentration of the hydrogen is going to be minus X. Now, because the change in hydrogen is going to be equal to the change of iodine, it's also going to be minus X. And from the molar ratio, then the concentration of HI will be plus 2x. Okay, for it's a 1-to-1 to 2 molar ratio. So far, so good. Okay, so we know the initial concentration is 0.2. So at equilibrium, it's going to be 0.2 minus the change, or x. It's going to be the same for iodine, and therefore for hydrogen iodide, it'll be 2x. Okay, so now we have our variables, our values to put into the equation, and we just have to solve for x. Okay, so that's the equilibrium constant rate equation. Plug in the variables as x, and then solve for x, because we know that the overall equilibrium constant is 49.5. So using a bit of algebra there, you can see that x equals 0.156. Okay, so hydrogen and iodine also, because it's a 1-to-1 mole ratio, will just be essentially 0.2 minus 0.156, or 0.044 moles per decimeter cubed, or molar. Okay, and the concentration of HI will be, of course, twice the value for x, which will be 0.312 molar or moles per decimeter cubed. Okay. Now, what happens when you have an equilibrium constant which is very small? Okay, less than 0.0001 or 10 to the minus 3. Okay, so the equilibrium constant for this reaction of nitrogen plus oxygen giving 2 nitrous oxide is 4.8 times 10 to the negative 31. Okay, quite a small number, as you can see. So initially there were 0.033 moles of nitrogen and 0.00810 moles of oxygen. How many moles of nitrous oxide are there in equilibrium? Okay. Well, again, we're doing the Rice analysis. You have a balanced equation, so you're basically just plugging in the variables. So the three components are your nitrogen gas, your oxygen gas, and your nitrous oxide gas. Okay, and then we have the ratios again, 1 to 1 to 2. Okay, 1 mole of nitrogen reacts with 1 mole of oxygen to give 2 moles of nitrous oxide. Okay, and we're given in the question the initial concentrations. So you've got 0.033 molar of moles of nitrogen and 0.00810 moles of oxygen. And obviously that's going to be 0 because nitrous oxide hasn't been made yet. Okay, so then we go back to our Rice table. Okay, filling it in. There we go, there we go. Okay. So again, we have the change in concentration as being minus X. Oxygen is going to be minus X as well, and nitrous oxide is going to be plus 2X. And therefore, at equilibrium, it's going to be 0.033 minus X for nitrogen from the question given, and 0.00810 minus X for oxygen. And nitrous oxide is going to be 2X. So again, we're going to be using algebra, because we know the equilibrium constant is given by the following equation. You plug in the values as if X, okay, and we know that it equals 4.8 times 10 to the negative 31. Okay, so there we have a equation there. So, for a small Kc, the numerator is small and X must be therefore small. So X is negligible when adding or subtracting. Okay, so that's the difference when it is less than 1 times 10 to the negative 3. Okay, so we basically, in terms of the numerator, ignore X. Okay, so we just completely take X out of the numerator. So it just becomes 2X all squared divided by 0.033 times 0.0081, because it's just so small. Okay, and that will also equal the 4.8 times 10 to the negative 31. So 2x squared equals 1.28 times 10 to the negative 34. You solve for x, and you get this as being the equilibrium number for NO. Okay, because that's going to be obviously 2x, because it's making 2 moles of the 2 moles of nitrous oxide. Okay, so hopefully that didn't make that made sense. Okay, so just basically for small Kc, numerator is really small, so you don't worry about x. So just to link this all together, let's look at the Gibbs free energy in relation to equilibrium constant. So the equilibrium constant gives an indication of Gibbs free energy. If K is 1, then the equilibrium, it's going to be an equilibrium, and the delta G is going to be 0. It's going to be at a minimum. And if the equilibrium constant is greater than 1, then the products are favored, and the change in Gibbs free energy is going to be less than 1. And if the equilibrium constant is less than 1, then the reactants are favored, and the change in Gibbs free energy at least is going to be greater than 1. Okay, that's kind of a summary. So we can use this information to find the following mathematical relationship, which is also found in your data booklet. So it's basically the standard change in Gibbs free energy equals negative gas constant times the temperature natural log of the equilibrium constant. And if you rearrange for K, then the natural log of the equilibrium constant is going to be the change in the standard Gibbs free energy divided by RT. Okay, so the gas constant times temperature. So just to finish off this topic, we'll just use that information to answer a problem. Okay, just to finish up, let's look at a problem involving the equation we just looked at. So determine the equilibrium constant for the following reaction at 300 Kelvin, given that the change in enthalpy is minus 824.2 kilojoules per mole, and the change in entropy is minus 270.5 joules per Kelvin per mole. Ooh, a negative entropy. And this is the equation, so basically it's rust. Okay, so what's going to be the equilibrium constant for the rusting of iron at room temperature, basically, given the following values. Right, so the first thing you should see is that we'll need to have a value for delta G. Okay, so delta G is going to be delta H minus T delta S, which if you plug in the numbers will give you a value of 743.1 kilojoules per mole. Okay, so that's going to be a positive value too. And if we then plug that number into the equation that we've just discovered, okay, you get a value for the natural log of K of 298, and then that means that the equilibrium constant is going to be e to the power of 298, or 2.6 times 10 to the 129, quite a big positive number. So that suggests, surprisingly, that the rusting of iron in the presence of oxygen at roughly room temperature is highly favorable. Surprise, surprise. And that's pretty much all there is about this topic. There's some further notes in your textbook around the reasoning behind why delta G is 0 at equilibrium, but I will leave you that for further reading.